Welcome back to topic 40 for Algebra 2, adding and subtracting rational expressions. In part 1, we're going to identify what is the least common denominator, how can we add and subtract rational expressions with like denominators, and how can we identify the least common multiple. So first we need to identify a common denominator in order to add and subtract rational expressions. Now we're going to start off with some easy examples here. If we have 1/4 and 3/8, how can we simplify? Well, we need a common denominator, so is there another way that we can rewrite either fraction? We can rewrite the first fraction, 1/4, as 2/8 because they are equivalent. Then we can add it to 3/8, and since they have a common denominator, we can add our numerators and get our sum of 5/8. Now example number 2 is a little bit different. Here, we don't have to think about factors because 3 is not a factor of 7, whereas in example 1, 4 was a factor of 8, so we could rewrite it that way. Example 2, what we can do is we can multiply our first fraction, top and bottom, by 7/7. And we can take our second fraction, 2/7, and multiply the top and bottom by 3/3. Now we can do this because 7/7 and 3/3 just simplify to 1. And if we multiply 1 by a value, the value doesn't change. After we find the product of these two individual fractions, we can rewrite them as 7/7 times 5/3 gives us 35/21. We can add that to 2/7 times 3/3 gets us 6/21. Now we have a common denominator and we can add them. So we get 41/21. Now for both examples, 5/8 and 41/21, we can't simplify this any further, so our answer is all set. So how do we find the least common denominator, also referred to as the LCD? In some examples, we can list all of the multiples of each denominator and pick the smallest. In example 1, we were looking specifically at the factors of them, since 4 was a factor of 8. Whereas in example 2, it's a little bit different. Sometimes we need to multiply the denominators. Now you can always multiply the denominators. It's just sometimes you might deal with really big numbers in the denominator. So if you can identify any other multiples that they both share and pick the smallest, that might be easier. Now let's look at some rational expressions and list any factors that can cancel. In example number 1, we have x times x plus 5 divided by x plus 5. Here, they both share a factor of x plus 5. So it will cancel since it's in both the numerator, and the denominator. In example number 2, we have 16x divided by 4. Now it's not as explicit as in example number 1 where we can obviously see, oh, there's an x plus 5 and an x plus 5 in the numerator and denominator. Here we have to think about those factors. Well, 4 goes in both to the numerator and denominator, and the problem actually simplifies to 4x divided by 1. So the factors that cancel would be 4. Looking at example number 3, we have 3 plus x plus 2 all over x plus 2. Now at first glance, you might think, oh, well, I can just easily cancel out x plus 2. Not so fast. Because x plus 2 is not in each individual term in the numerator, we can't cancel it. We cannot factor it out and cancel it. It's only in one of the terms in the numerator. So here we have no factors that cancel. Moving on to the next examples, here we're adding and subtracting rational expressions with like denominators. So what I like to do first is just rewrite each example so that we have a common denominator across the board. So we can rewrite this as 12 minus 2 all over 5x. Our numerator simplifies to 12 minus 2, or 10, over 5x. And here we have a common factor of 5 that goes into both the numerator and denominator. So if we divide the numerator by 5, we get 2. And if we divide the denominator by 5, we get 1. So our new answer is 2 divided by x. Now thinking back to topic 39, where we identified restrictions on the denominator, here remember our denominator can never equal 0. So our variable of x can't equal 0. Moving on to example 2, we have x squared divided by x minus 2 plus x plus 2 divided by x minus 2. So because we have a common denominator of x minus 2, we can write that and write our numerator as x squared plus x plus 2. Now sometimes we can factor the numerator and cancel. However, here we can't actually factor the numerator to cancel with the denominator, so we can just leave it as is. We can, however, identify any restrictions that we have in the domain. So x minus 2 cannot be equivalent to 0, so we know that this exists for all real numbers except where x does not equal 2. Moving on to our third example, we have 2x plus 1 divided by x squared plus 3x plus 3x minus 8 divided by x times x plus 3. If we look at our denominator, at first glance they might not look the same. However, we can rewrite x squared plus 3x as x times x plus 3. So they actually do have a common denominator. Then we can combine in our numerators. So our denominator is x times x plus 3, and I personally like to keep it in factored form whenever possible because it's, again, really easy to identify restrictions on the domain. In the numerator, we will have the quantity 2x plus 1 plus 3x minus 8. So here we can combine our like terms. We have 2x and 3x, which gives us 5x. And then we have 1 and a negative 8, which gives us minus 7 over x times x plus 3. And this occurs for all real numbers where x cannot equal 0 or negative 3. Now, sometimes we need to identify the least common multiple. So what we want to do is we want to first factor each polynomial. Now, the least common multiple is the product of all of the factors. And sometimes we deal with factors that have an exponent outside of our parentheses. So those are identified as duplicate factors, and they occur as many times as the exponent says. So, for example, let's identify the least common multiple of these following polynomials. Our first example, we have x plus 2 squared. So just like I was referring to with our greatest power on the outside, x plus 2 means that we see that quantity twice. X plus 2 times x plus 2. Now our other polynomial, x squared plus 5x plus 6, we can factor. Well, multiply to get 6, but add to get 5. Well, we would have x plus 2 times x plus 3. So we want to identify the product of all the factors for the least common multiple. So we have to compare across all of these factors. Well, our first polynomial, x plus 2 squared, shows x plus 2 twice. So in our least common multiple, we need to have that x plus 2 occur twice. Notice if we look at the second polynomial, we see it just once. However, because we need to use both polynomials in order to identify the least common multiple, because it occurs twice in the first polynomial, in our least common multiple, we need to see it twice. Now our second polynomial also has another factor that's not included in the first polynomial. We have x plus 3. So in our least common multiple, we also need to include our x plus 3. All of these factors need to be accounted for. Then we can rewrite this as x plus 2 times x plus 2 times x plus 3, or x plus 2 squared times x plus 3. Looking at example number 2, we have 3 polynomials that we're dealing with. We have x cubed minus 9x, x squared minus 2x minus 15, and x squared minus 5x. We can rewrite the first polynomial by factoring out an x and getting x squared minus 9. Now this second part right here, x squared minus 9, that's the difference of squares because we're dealing with x squared, which is a square value, and we're also dealing with 9, which is a square value. So we can break this apart even further to be x times x plus 3 and x minus 3. Now this is called difference of squares because we're literally dealing with a difference here. We're dealing with subtraction. We can also think about it, difference, we're dealing with different signs. X plus 3 and x minus 3. Our next polynomial, we have x squared minus 2x minus 15. If we factor this, we will get x plus 3 times x minus 5. And our third and final polynomial, we have x squared minus 5x. So we can factor out an x times x minus 5. Oops, keep doing that. Now our least common multiple, again, we need to account for every single factor and however many times it occurs, the maximum times it occurs. So if we look through, well, we have an x here and an x here, so we need to include that. We also have an x plus 3, so we're going to include that in our least common multiple. Then we have an x minus 3. Looking at the next polynomial, we factored it to be x plus 3 times x minus 3. Now we already accounted for our x plus 3. However, x minus 5 is different. Our final polynomial, we have x times x minus 5. Now both our x and our x minus 5 are accounted for, so we don't need to include any more factors in this least common multiple. We are all set right here. Now I did want to make a note that each original polynomial that we dealt with for each of the problems is a factor of this least common multiple. And we can visually see that. In example number 2, we see an x plus 3, and we see an x minus 3 in our final least common multiple. With our second polynomial, we see an x plus 3, and we also see an x minus 5. With our third polynomial, we see our x, and we also see our x minus 5. And that is part 1 for topic 40 for adding and subtracting rational expressions.